So we now have a reduced order model of SEI growth. Is it any good? It's kind of an important question to ask before we decide how to use it in a control scenario. The validity of this model depends first on the underlying partial differential equation model that was proposed by Ramadas. So if the Ramadas model turns out to be a bad description of what's really happening in reality, then this reduced order model is going to also be a bad description, because all we're trying to do is we're trying to approximate that PDE model as well as we can. So here in this section, we will assume that the PDE model is exact. In actuality, there has been some more recent work since the Ramadas paper by Safari and colleagues, and probably others as well, that somewhat modifies the Ramadas model and says that it's possible to improve the model to get better predictions. And we've been working on making reduced order versions of those also. But for now, let's just assume this Ramadas model is a pretty good description of SEI growth. If we assume that, then the validity of our reduced order model depends on how closely our approximations match the Ramadas calculations. So we decided to investigate how well this worked by conducting some simulations. In each of the simulations, we talk about it first. The cell was initially at rest, and then we apply a pulse of current suddenly, and then the instantaneous resulting side reaction flux from the PDE model is compared to the computed value from the reduced order model. We did this because it matches all of our assumptions and all of the Ramadas assumptions, so it's a good place to start out. If you don't work very well in that case, you're probably not going to work in a more general setting either. To simulate the PDE model, we created a revised version of the ideal cell in COMSOL. This was done a while ago, so we used a somewhat older version of COMSOL that was available at that time. But we then had this COMSOL model that was coupled together with a MATLAB script that cycled automatically through a number of simulations so that we didn't have to run them manually. And the MATLAB script also analyzed the results of the simulations, so that was really important to be able to do. You'll see there were many, many thousands of simulations done overall. The input, or the simulation period, was a 1-second time interval. And in that 1-second time interval, the cell was initially at rest, and then halfway through, at time 0.5, we apply this pulse, this Heaviside step function. The initial rest period was helpful, we found, because COMSOL has to adjust all of the variables so that the equations match each other. So at the very beginning of time, it's spending some of that interval converging to a valid solution. So it didn't have to be maybe a full half-second long, but we did want to have some rest period before the pulse was applied to make sure the COMSOL was converged before we applied the pulse. Then we applied the pulse, and then we measured the side reaction flux immediately after the onset of that pulse. The parameters, if you want to build your own simulation, are listed in an appendix to this chapter. The cell had a 1.8 amp hour capacity. These parameters actually were the ones directly from Ramadas's paper, and we used the same ones as he did. For the full order simulations, we did simulations where the applied current was varied from 0 amps to 5.4 amps of charge current, that is. So I guess you could say it's minus 5.4 if you want to be really careful. In steps of 0.1 amps. And the initial cell state of charge varied between 0% and 100% in steps of 2%. And temperature was varied between 35 or minus 35 Celsius and 45 in steps of 20 degrees. The reduced order model ran a lot more quickly, so we could do more simulations. So we had the same range, except we did twice as fine steps of applied current and twice as fine steps of SOC and twice as fine steps of temperature. So basically 8 times as many simulations were done of the reduced order model as we did of the full order model. As one point of comparison, the if you figure out how many simulations were done, there was 14,025 full order PDE simulations. And this was all automated. It was all done in COMSOL with MATLAB calling COMSOL 14,025 times. It took more than 8 days to complete on an Intel i7 processor, which is still a pretty modern processor. The reduced order model simulations, there's 8 times as many, so 112,200 reduced order model simulations took a total of about 2.6 seconds on the same machine. 8 days, 2.6 seconds. And by the way, the reduced order model simulations were not coded up in anything fancy like C, and they didn't use multiple cores of the processor like COMSOL did. COMSOL used, I believe, 4 cores of the processor for 8 days, whereas the reduced order model simulations, single core of interpreted MATLAB, 2.6 seconds. That is the main advantage of the reduced order model. It's a speed up of more than 2 million to 1. This is why we would use a reduced order model instead of a PDE model inside of a battery management system, because I have to do stuff quickly or with limited computation because we want to do it cheaply. We have some figures plotted. It's interesting to look at them. One of the reasons for doing so many simulations was to get a feel for how the side reaction flux actually worked, to get a nice smooth picture. And on the left here, we have the side reaction flux versus state of charge and charge current. And so charge current getting bigger is this way, and state of charge getting bigger is that way. And the flux, remember, a bigger negative number is bad. So red is bad, blue is good. And we can see that increasing the charge current makes the film grow faster, and increasing the state of charge at the beginning of the pulse makes the film grow faster also. Starting at very low states of charge, there's very little film growth, and at low currents, there's very little film growth also. Picture on the right shows these results for many different temperatures overlaid on each other. Ramadas did not give temperature-dependent parameters for everything, so this may or may not be strictly correct. However, we computed using the reduced order model and the full order model the same sets of parameters for both, so it should be a valid comparison whether or not we have the right temperature-dependent values in there. What's not clear in these pictures is that I'm showing you both the reduced order model and the full order model in every case. The reduced order model was so close you can't tell them apart unless you zoom in. And so some of the results we're going to look at coming up are kind of zooms in, or different ways of looking at these overall results so that we can see where they may be somewhat slightly different. The figure on the right shows the results of one PDE and ROM simulation, just so that we can look at them together. So of course the first half second is the period where the cell is resting, and the next half second is where the pulse of current has been applied. And we start at some resting side reaction rate. As we said, we relaxed Ramadas' assumption to say that side reactions could occur even when the cell is resting, although we expect them not to occur very quickly. And then the non-resting rate, when I'm charging. And this is a 1C charge pulse in this example. If you can see, there's a solid line there and a dashed line. The solid line is the PDE result, and the dashed line is the reduced order model calculation. And they're very, very similar. And in particular, we were comparing this number right there, right at the onset. But even after a half second, we see that there's not much difference between them. The PDE model does not change very rapidly over time. So I think we said all of that. If I plot on the same scale the PDE solution and the ROM results as I did on the top of the page, it's impossible to tell them apart. So to compare them, we defined a relative error, which is the PDE result minus the ROM result divided by the PDE result. times 100 to give you an error in percentage. So truth minus estimate over truth times 100, which is the common way of doing it. And plotting the relative error versus state of charge versus charge current, we get this picture here. And we see that in one range there's noticeable error, but for most of the operating range of this cell there's minuscule error, less than 0.44%. So between states of charge of 10% and 90% SOC, which is typical operating conditions for an electric vehicle kind of application, the maximum relative error was 0.44%, which is very, very low. And then the places where the error was bad was when the state of charge was low. And that's when you really don't expect very much SEI growth at all, because it only happens on high charging events close to 100% SOC. So maybe I don't even have to worry about the relative error there compared to the error, if I had relative error when SEI growth was very rapid. We can also look at the comparison between full order model and reduced order model in these pictures here. And I'm afraid that at this zoom level it's not going to be possible to see, maybe not even then. Hopefully you can zoom in on your notes if we can't see it here. I can't even see it here. Maybe you're able to see it, but every one of these colored lines is in fact two different lines. There's a solid result from the partial differential equation and a dashed result from the reduced order model, and they're so close to each other I can't distinguish them. So maybe if you have the the PDF, not PDE, if you have the PDF, you can zoom in. These should be vector graphics, so you should be able to zoom in until you can see some slight difference, but they're that close to each other that they match very well. So these results I'm plotting here are slices through that three-dimensional plot that was on the top of the prior page. So these are slices when state of charge varies for different C rates, and these are slices for different C rates at different SOC values, so you can kind of see what the profile of that 3D plot looks like when I take these different cross sections. So clearly low rate causes less degradation than high rate, and SOC is a major effect, or has major impact, that when I'm at high states of charge the side reaction is much worse than at low states of charge. And here we can see again that for the C rate has kind of an impact. If I have this 100% state of charge curve, for example, the higher the charge rate I use, the faster the film grows. And there's this kind of growing slope, whereas for low states of charge there's very little film growth rate and there's very little SOC dependence there. What's interesting here is notice that this curve is starting at 100% state of charge and it's saying let's do a charge pulse. I can charge the cell above 100% state of charge. It just is causing high degradation when I do it. So if I rest at that state of charge, there is some degradation. Just because I'm at that high state of charge, that high voltage, there's some degradation. But if I try to charge it faster, there's going to be a lot more degradation. So it would make sense to not leave the cell at such high states of charge, but to try to find some kind of a happy medium state of charge where you want to park your cell. And you've probably heard it said that you don't want to charge your laptop battery to 100% and leave it there. Of course, I do that anyway, but the reason is, if I keep my laptop half charged most of the time, then my degradation due to this mechanism is going to be much lower than if I have my laptop fully charged most of the time. It actually makes the battery last longer. So we talked about those results. We have results that are nearly indistinguishable between the ROM and the full order model. We can plot results versus temperature here, so I invite you to look at those, and we see that The predictions turn out to be best at high temperature and relatively best and relatively worst at low temperature. But even so, the worst case in the normal operating range is in the order of 0.5% relative error, which is plenty accurate enough to do some very interesting controls with. So temperature doesn't have a big negative impact on the results. The way you say, well, one of the assumptions you made was that the pulse would last would be instantaneous, and you showed it for only half a second. Well, what if we increase the length of the pulse? Okay, so we can look at that as well. So instead of looking immediately after the application of the current pulse, I look at the end of the simulation at 0.5 seconds, and we get these kind of relative errors. And it's on the order, worst case, of about 1% relative error when I do that. So that's really quite good also. You could say, well, when I'm charging a battery cell, I'm not charging it from equilibrium and doing a short pulse. I'm actually charging over a very long period of time, like maybe an hour or so. And in this plot, we look at the PDE result of the side reaction flux plotted versus the dimensionless distance across the anode. So this is z equals 0 and this is z equals 1, if you remember the z coordinate system. And the PDE result is solid. The average of the PDE is the dashed line, and the dot dash line is the reduced order model calculation of the average. And we see that after 100 seconds, they're hard to discern. After 1,000 seconds, they're hard. 2,000, a little difference. 3,000 seconds of constant charging, starting at 0% SOC, we can begin to detect some difference between the spatially dependent 1D model and the reduced order model, but it's really, really small differences. And the difference between the two averages is, in fact, hard to tell apart. So even after 3,000 seconds of not being at rest, this reduced order model gives really good results for these parameters. So overall, the simulations have validated that the reduced order model seems to provide results that make sense, at least compared to that full order model. And it's much faster. So this is the kind of model that we want when we're doing optimized controls. So we'll talk about optimized controls in a few sections, but now you see at least one example of how we developed from the very beginning PDE model, a reduced order model that gives pretty high fidelity at much faster computation, and we can use it to extend lifetime of our cell, we hope.